Over the last few lectures, we have been taking a look at the representation theory for groups. We have looked in particular at the great orthogonality theorem and its consequence, the character orthogonality theorem. And in the process, we had met the character vector. Let me just remind you that the character vector for a given representation is defined to be a vector which has as many elements as the number of classes of the group, and so there is one element for each class, and the element for a given class is nothing but the character for any group element belonging to that class multiplied by a normalizing factor, which is square root of the number of elements in the class, NCI, divided by the order of the group. Now, the reason why we use this rather clumsy looking normalization is that as a result of this, what the character orthogonality theorem takes this particular form. If you add up over all the classes, I running from 1 to nc, chi alpha I times chi beta j star, you end up with delta alpha beta. Let me remind you here, chi alpha I is for an irrep alpha labeled by alpha, and the ith component here is chi alpha ci times square root of nci by mod g. So when I write the ith component of the character vector, I already have the normalization factor built in. It's not just a character for the ith class, it's the character for the ith class multiplied by square root of the number of elements in that class divided by the order of the group. Of course, you can define a character vector for any representation, but character vectors become especially important for irreducible representations. And if alpha and beta are two inequivalent irreducible representations, then you end up with inequivalent or identical. That is, if alpha equals beta, they are identical. If alpha is not equal to beta, they are inequivalent. Then you have this result that chi alpha I times chi beta j star is delta alpha beta. Now this sum makes it obvious that this is an inner product. And so we can of course use this notation, the inner product notation of an inner product between two vectors chi alpha and chi beta. And what the result essentially becomes, inner product between chi alpha and chi beta is simply delta alpha beta, and hence the character vectors for irreducible representations form an orthonormal set. At this point, let me stress that the inner product that we have defined here is essentially the sum of chi I, chi j star kind of inner product. This is basically consistent with the way mathematicians usually define inner products on complex vector spaces, or Hermite products to be more precise. These are linear in the first factor and antilinear in the second factor. Physicists are usually more used to an inner product which is defined in a slightly different fashion. The physicist's inner product is typically defined to be linear in the second factor and antilinear in the first. This is more of a result of exposure to quantum mechanics, where the integral psi star phi kind of, where the integrals we use are of the form integral of psi star phi over some measure, and so it's naturally linear over the second factor phi and antilinear over the first factor psi. And it is this quantum mechanical legacy which makes physicists use an inner product which is antilinear in the first factor rather than linear in the first factor. Our inner product here is more like linear, is more like the mathematicians. It is linear in the first factor, antilinear in the second. But be that as it may, the upshot is the character vectors for irreducible inequivalent representations are orthogonal to each other. At this point, I think I should warn you that I have been guilty of changing my notation here. In the last lecture, I had referred to this particular inner product using the chi alpha dot chi beta notation. I had used the standard dot product notation for the inner product. The reason why I have chosen to change that is simply that this particular inner product is not really exactly the same as the dot product in ordinary 3D real vector spaces. There is this conjugation on the components of the second vector which we have to worry about, and it's perhaps best to use a different notation in order to avoid confusion with the ordinary dot product. But I'm sure you can all take this change of notation in your stride, and if I ever lapse into using the dot symbol for this particular inner product, I hope it will not be too much of an inconvenience to any of you. An immediate upshot of this orthogonality relation is that the character vectors belonging to distinct inequivalent irreducible representations are all linearly independent. Now that actually is a very important point. Notice the dimensionality of our space is the same as the number of classes that the group has, and this immediately tells us that the number of irreducible representations a group may have is bounded above by the number of its classes. But we are going to claim something more. We are going to claim that these character vectors for irreducible representations, taken together, they are also complete in the space of class vectors. Class vectors are simply vectors with one element for each class of the group. That means essentially a vector with nc number of elements, like our chi vector here. What I'm claiming is every vector with nc components can be expanded in terms of these character vectors for irreducible representations. So let us try to check whether that is true. But before we do that, let us ask ourselves, what will the condition be that will tell us that this is true or not? So if a class vector, a vector which has nc elements, f1, f2, fnc, we are calling it a class vector simply because we are assuming that each one of these values, f1, f2, etc., are values which is obtained for when you take elements from a given class in a group. So all group elements belonging to the same class contributes the same amount. For any such function, you are going to get a class vector. Let us assume that a class vector f can be written as a linear combination of the chi alphas. So it can be a sum over alpha. We already know that this is a finite sum because the number of irreps cannot exceed the number of classes of a alpha times chi alpha. At this point, we are not saying that all vectors which are class vectors, all vectors with nc components, can be written down in this form. But if a particular class vector can be written down in this form, we can immediately see that a alpha can be found out by using the orthogonality relation which the character vectors have. So if you just take the inner product of the vector f with the vector chi alpha, it trivially follows from the orthogonality relation that this inner product has to be the coefficient a alpha. This is something which is very familiar to all of you. Say if you want the x component of a vector, all you have to do is take the dot product with I, the unit vector in the x direction. This is exactly that result in a more general context. Now, of course, once we have a alpha, we can put it back and get an expression for f. So f works out to be sum over alpha chi alpha times the inner product of f with chi alpha. If I try writing this equation in terms of components, the ith component of f will be fi is equal to sum over all alpha chi alpha I times the inner product. And if I replace the inner product by the sum over j of fj chi alpha j star and interchange the sums over alpha and j, what I am going to land up with is this expression for fi, which is fi equals sum over j fj times something, and that something is sum over alpha chi I alpha chi j alpha star. So far, we have assumed that a given class vector f can be expressed as a linear combination of the character vectors chi alpha corresponding to the irreducible representations. And that has led us to this particular expression. But if this expression is to work for all class vectors fi, then the factor in the bracket there must take a very specific form. If fi is to be the sum over j fj times something for no matter what fj's I choose, the only possible way that can happen is that this thing in the bracket, the sum over alpha of chi I alpha chi j alpha star, must be equal to delta ij. So, if our character vectors for irreducible representations form a complete set over and above being an orthogonal set, then you must have this result that chi j alpha conjugate summed over all possible irreps must give you the delta symbol. The question is this at all true? And that is what we are going to try to answer next. And our tool here is going to be what else? The great orthogonality theorem itself. We are going to start with a slightly specialized version of the great orthogonality theorem, a version where we are talking about the same irrep. That is, the irrep label alpha is equal to beta. Now, in this version, the orthogonality theorem simply takes this form: d alpha ii prime for a particular group element G times d alpha j prime j for the group element G inverse. When you sum this quantity over all group elements, you get mod G by d alpha times delta ij times delta I prime j prime. Let me stress that here I prime, j prime and j are all free indices. You are free to give them any specific value you want, you are free to sum up over them, or you are free to do other manipulations over them. And we are going to exploit this free nature of these indices to insert two more matrix elements in this particular problem. I am going to choose two arbitrary elements G1 and G2 from the group capital G and take the matrices corresponding to G1 and G2 in this particular representation and insert the elements in between this expression and sum up over the indices in such a way that I am going to be able to form a product of a overall matrix. So let's just see what I mean by this. What I am doing is I have inserted some new things which are written in red here. D alpha I prime j prime G1 has been sandwiched between the original two terms in blue, and on the right I have written d alpha ji G2 inverse. Notice that the way the indices have been placed, I prime d alpha I prime G followed by d alpha I prime j prime for G1, then d alpha j prime j for G inverse, then d alpha ji for G2 inverse is exactly the correct order in which things should occur for matrix multiplication. And in order to do that, I am actually summing up over I prime j and j prime. Of course, if I had summed up over only these three indices, then what I would have ended up with is the d alpha ith element corresponding to the group element G, G1, G inverse, G2 inverse. This, of course, is simply a result of the fact that d alpha is a homomorphism, so it respects group multiplication. Since I am also summing up over I, this really gives us a trace. Now I am going to do exactly the same thing to the right hand side also as well. That is, I am going to multiply by d alpha I prime j prime G1 and d alpha ji G2 inverse and sum up over I prime j and j prime. These new things that I have put in has been indicated in red here. Now, if you carry out the summation on the right, because of the presence of the delta symbols, it's very easy to do. Delta ij will force the two indices on d alpha ji G2 inverse to become the same index, so you will get d alpha ii G2 inverse, and then you have to sum up over I, and that of course gives the character for the element G2 inverse. And very similarly, the delta I prime j prime is going to make d alpha I prime j prime G1 sum up to chi alpha of G1. So taking all that into account, what we have on the left hand side is a sum over all group elements of the character in the alpha irrep of the group element G, G1, G inverse, G2 inverse. And on the right hand side, what we have is, apart from the factor mod G by d alpha, just two characters chi alpha G1 times chi alpha G2 inverse. Now, the reason why this is so useful is that what we can next do is rewrite the chi alpha G1 chi alpha G2 inverse by bringing in the factor d alpha by mod G to the other side. And not only that, I can actually write chi alpha G2 inverse as chi alpha G2 star. Note that what we wanted in our completeness relation proof is that what we have is chi alpha j star sum over all alpha. We don't have a sum over alpha yet, but we already have chi alpha g1, chi alpha g2 star. Well, g1, g2 are of course just group elements. We will have to see the connection between this and classes soon. But what we need to do is we need to rewrite this expression, or we need to sum up this expression over all alpha. And that leads to this particular expression. Now, the left-hand side is beginning to look more and more like what we want of our completeness sum. What about the right-hand side? On the right-hand side, what we have is a quantity which is a sum over all alpha of d alpha, chi alpha of a particular thing. But if you remember the regular representation contains all irreducible representations exactly as many times as the dimensionality of that representation. So the sum over alpha d alpha chi alpha for some group element is nothing but the regular representation character chi reg of this quantity of this group element g1, g inverse, g2 inverse. Of course, there is still the sum over all group elements, and this is division by the number of group elements. Basically, this expression chi reg g1, g inverse, g2 inverse has been averaged out over the entire group. In order to proceed any further, let me remind you of a basic property of the regular representation. In the regular representation, the group elements essentially acts on a vector space whose bases are the group elements themselves. So the dimensionality of the space is nothing but the order of the group. And in this representation, only the identity is labeled by an identity matrix. All other group elements are represented by matrices which have only zeros on the diagonal. As a result, for the regular representation, the character is given by this simple expression. It is equal to the order of the group if the element G that we are talking about is the identity, and if we are talking about any other element, then the character is simply 0. So, what we see here is this. The sum that we have on the left hand side essentially equals a sum of the regular representation characters for a particular combination G1, G inverse, G2 inverse. Now, this means that this sum vanishes unless there exists at least one small g belonging to the group capital G such that G1, G inverse, G2 inverse is the identity. Because remember, for all other group elements, the regular representation character is 0. Now, of course, if G1, G inverse, G2 inverse is the identity, that's the same thing as saying that G2 is G1, G inverse, that is, G2 belongs to the same class as G1. Hence, the sum on the left hand side vanishes unless G1 and G2 belongs to the same class. And now, what we can always do is replace chi alpha G1 by chi alpha Ci, where Ci is simply the ith class to which G1 belongs. And if G2 belongs to the jth class, then the expression on the left can be written down as a sum over all irreps of chi alpha for the ith class Ci times the character chi alpha for the jth class Cj conjugated. When you sum it up over all irreps, you end up with delta ij times some number, which of course can depend on the particular class that we are talking about. That is, if G1 and G2 belong to different classes, this sum is 0. If G1 and G2 belong to the same class, that is, if I and J are equal in the sum above, then this expression has to be an integer. A moment's thought will show you that this integer is nothing but the number of group elements small g such that G1, G inverse is exactly equal to G2. We can find out the constant lambda I in this expression above simply by answering this group theoretical question. If you take two elements G1 and G2 from the ith class, how many elements small g are there in the group capital G such that the conjugation of G1 by small g leads to G2. We can find out this number from purely group theoretical considerations. For example, you could argue along these lines. If G G1 G inverse and G prime G1 G inverse both were equal to G2, then it would follow that G inverse G prime commutes with G1. In fact, it implies that G inverse G prime is an element of a set of those elements of the group capital G which commute with G1, a set which is known as a centralizer of G1 and which you can show very easily is a subgroup of G1. From here, you can easily see that two elements, both of which lead to the conjugation of G1 into G2, would actually belong to the same coset of the centralizer subgroup. And proceeding along these lines with a bit more basic algebra, you can figure out the number lambda I. We will do it in another way simply because we have access to the character orthogonality theorem and we can simply apply it to find out lambda I by using the character orthogonality theorem in this particular sum. The way to do that would be simply this. You multiply both sides by the term written in red, that is n Cj, number of elements in the class Cj, times chi beta Cj, where beta is some irrep. And then you sum up over j. Of course, when you sum up over j, the sum over j on the left is exactly the sum that you carry out in the character orthogonality theorem. So that is going to be mod g times delta alpha beta. On the other hand, on the right hand side, the presence of the delta ij makes the sum over j rather trivial. You are going to get lambda I nci chi beta ci. And this will simply simplify to the expression sum over all alpha chi alpha ci times mod g delta alpha beta. This of course comes from the character orthogonality theorem, and that's equal to lambda I times nci times chi beta ci. Now the summation over chi alpha ci delta alpha beta, the summation over alpha is again trivial because of the delta alpha beta, and you end up with chi beta ci times mod g is simply lambda I times nci times chi beta ci. And now you can simply cancel out the chi beta ci from both sides and you are going to end up with the result that lambda I is mod g by nci. If you are being very careful, you might just object here saying that what happens if chi beta ci, the character of for the ith class in the betath irrep, is actually 0. Then of course cancellation of chi beta ci on both sides will not be valid. But note that this expression that we have obtained here is independent of which irrep we are talking about. And in particular, we at least have one irrep for every group where the character is not 0. This is, of course, the trivial irreducible representation, the one-dimensional irreducible representation where every element of the group is mapped to the number 1. Hence, the corresponding character is just the number 1, which definitely is not 0. So, even if you do have some particular irrep for which the ith class has a 0 character, that does not change the fact that this calculation will simply go through. And you will get lambda I equals mod g by nci, irrespective of which irrep you actually used in this particular calculation. Now, once we have the value of lambda I, we can of course plug it back and get an expression for the sum over alpha of chi alpha ci, chi alpha cj star. That, remember, was lambda I delta ij. Now lambda I is mod g by nci, the number of elements in the group divided by the number of elements in the ith class. Please try to arrive at the same result by using the group theoretical argument that I just described a while ago, using the concept of the centralizer of a group element. Now, once we have got this particular result, it is pretty easy to see that because of the presence of the delta ij term, you could very well write mod g by nci as square root of mod g by nci into square root of mod g by ncj. Remember, this expression is non-zero only when I is equal to j, and therefore square root of mod g by nci times square root of mod g by ncj would effectively be the same as mod g by nci. We will then just move these square roots to the other side and we will end up with the formula sum over alpha square root of nci by mod g chi alpha ci times square root of ncj by mod g chi alpha cj star summed over all alpha. Note that the square roots can of course move into the sum because they are completely independent of the summation index which labels different irreps. And this sum of course has to be delta ij. But the reason why I have written this in this particular form is to sort of emphasize that chi alpha ci times square root of nci by mod j is nothing but chi I alpha, the component of the character vector, the orthonormal character vectors that we used. And the next entry is just chi j alpha star. And so what we have ended up with here is that if you sum up over all irreps, chi I alpha times chi j alpha star, you are going to get delta ij. Let me just remind you, a while ago I had established that this is exactly the condition you need the character vectors to obey in order that the character vectors form a complete set. And this completes our proof that the character vectors are not only a linearly independent set, they are also a complete set in the space of class vectors, and therefore they together form a basis of the space formed by the class vectors. And since the number of elements in a basis has to be equal to the dimensionality of the space, it follows immediately that the number of character vectors, hence the number of irreducible representations a particular group can have, has to be equal to the number of its conjugacy classes. This particular result is one which we have referred to several times in earlier lectures, and we have even used it when we tried to construct the entire character table of S3 from scratch. But this is the first time we have actually proven this result. Now, from what we have described over the last few lectures, it should be obvious that the character table, that is a set of characters for each irreducible representation of a particular group, is a very handy tool to have. And once you have such a table, you can put it to all sorts of wonderful uses. As I have mentioned a while ago, we had actually built up the character table for a particular group, namely S3, from scratch, but there all we used was the character orthogonality theorem, some basic properties of characters like the fact that characters are class functions, as well as some basic ideas about the nature of the particular group itself. Now, while this technique worked fine for a small group like S3, for more complicated groups, this kind of technique would actually be very, very difficult to use. Now, since this is such an important topic, there has been a lot of work on the process of building up a character table from scratch, and there has been a lot of progress in building various algorithmic techniques which will, given the structure of the group, immediately find out all its characters through some kind of well-defined process. Now, we are not in a position to discuss all these techniques in this course because that would be a course in itself. But what I am going to do is, I am going to at least give you the flavor of one such method, the so-called Burnside method for finding out the characters of a group. Now, the basic ingredient in the Burnside method is the concept of something called a class vector. And to understand this, we have to go back to the notion of the group algebra generated by a group. Remember, we had actually been able to convert a group into a linear vector space just by considering formally all linear combinations of group elements. And class vectors essentially reside on this particular vector space. So the way in which we define a class vector is simply, we add up all the group elements belonging to a particular class and this gives us the ith C vector or C vector I. Here I runs from 1, 2 all the way up to the number of classes. So you have one class vector for each class. So just as an example, in S3, you had 3 classes. C1 had only the identity in it. So C1 vector would just be the identity. Remember, within the context of the group algebra, the group elements are also vectors. For C2, the second class, we could take the 2 rotations, 2 non-trivial rotations, D and F. So C2 vector would simply be D plus F. For C3, the third class, we have A, B and C, the 3 reflections as elements, and C3 vector would simply be A plus B plus C. So these are our class vectors. Now, if you consider a particular matrix representation of the group, this representation may or may not be irreducible, but any general matrix representation, then corresponding to the ith class vector, we can also define a class matrix, which is simply the matrix I get by adding up D of G, where G runs over the entire class. So you have one class matrix for each class. In S3, you will have 3 class matrices, D1, which is D of E, D2, which is D of A plus D of B plus D of C, and D3, which is simply D of D, small d, plus D of F. Now, these class matrices have a very special property. If you take any group element from capital G and consider the matrix D of G and use this matrix to carry out a similarity transformation on Di, that is, you form the matrix D of G, Di, Dg inverse, then this simply is of course Dg times sum over the entire class Ci of Dg prime times D inverse. This is a case where I can easily move the D of G and D of G inverse inside the sum and use the fact that these are representations to rewrite this sum as sum over the entire ith class, as G prime runs over the entire ith class of D of G, G prime, G inverse. Now it is very easy to see that for any fixed small g, as G prime runs over the entire class, G, G prime, G inverse also runs over exactly the same set of elements in some other order. And thus, in this process, the sum gives you back exactly Di. So the upshot of all this is, D of G, Di, D of G inverse is Di, and that is, Di is a matrix which commutes with D of G for each small g in capital G. Now this should immediately remind you of Schur's lemma. A matrix which commutes with every matrix in an irreducible representation of a group must be a multiple of the identity. Of course, this result that we have, that D of G commutes with Di for all small g belonging to capital G, is valid for all representations, reducible or irreducible. But if my representation happens to be an irreducible representation, let's say the alphath irreducible representation, then Schur's lemma will immediately tell me that the Di corresponding to the alphath representation, Di alpha, must be a multiple of the identity. So it must be identity times a constant, which depends of course on the class I and which representation you're talking about. So lambda I alpha. Now these numbers lambda I alpha are actually related to the characters and they are called Dirac characters. Another name for these are class constants. So to summarize, what we have found out is that if I start with any irreducible representation of a group and add all the matrices corresponding to a given class, I am going to get a matrix which is the identity matrix into a coefficient, and that coefficient is our class constant for that particular class and that particular irrep. Now the reason why we are so interested in the Dirac characters is simply that they are related to the characters that we have been dealing with so far. And that is easily seen by taking a trace of the ith class matrix. So if I take the trace of di alpha, what you are going to get is simply the sum of the traces of all the representation matrices which go into making up di alpha. That is, you have to sum up the characters of all the group elements in the alpha arep, of course. But note that each and every one of these group elements belong to the same class, namely Ci, and therefore they contribute exactly the same amount. All the characters that go into this sum are the same. So what you get is simply the character corresponding to the ith class chi alpha Ci times the number of elements in this sum, which is simply nci. So what I get is trace of di alpha is nci chi alpha Ci. On the other hand, di alpha, as we have already seen, is lambda I alpha times the identity matrix. So its trace is obviously lambda I alpha times the trace of the identity matrix, which is d alpha, small d alpha, the dimensionality of the alpha arep. So this expression nci chi alpha Ci is the same as lambda I alpha times d alpha, and this immediately tells me that the character for the ith class is simply given by d alpha by nci times lambda I alpha. So if you knew the dimensionality of the representation, you could just use the Dirac characters to find out what the characters corresponding to a particular class is. The only hitch here is that if you are doing this entirely from scratch, you would not know what the dimensionality of the alpha arep is. But that is easily remedied. To see how the Dirac characters can also tell you about the dimensionalities of the areps directly, let us start from the irreducibility criterion. Remember, the irreducibility criterion says that if you took the chi vectors, the character vectors, and to form the inner product of a character vector of an irreducible representation with itself, you are going to get 1. Or, equivalently, if you were to take chi alpha Ci's, the characters for the ith class, took their square modulus, weighted them with the number of elements in the class, added up over all the classes, you would get the order of the group. Now, since we have already seen that chi alpha Ci mod square is given by d alpha by nci lambda I alpha, substituting that here will give me the result that mod G is d alpha square times the sum over all classes of this quantity. The Dirac character mod square divided by the number of elements in the class. And this can be easily rewritten to find out an expression for d alpha. D alpha square will turn out to be mod G divided by sum over I going from 1 to nc of lambda I alpha mod square by nci. And this immediately tells us that if you knew all the Dirac characters for a particular group, from that you would be able to find out both the dimensionality, which the second formula in red will give us, and using the dimensionality and the Dirac characters, you can actually go back and find all the characters. So building up the character table is equivalent to finding out the Dirac characters. And this is essentially the idea behind the Burnside method. That is, we will derive an approach for finding out the lambda i's, and from there we are going to find out the dimensionalities of the areps and the characters of the areps. Now, Burnside's method depends on a particular property of these class vectors. Before I go on to describe the method in detail, let me just talk about a particular example that will make this property clearer. And what other example can we talk about rather than our old friend, the group S3. As I've already said, S3 has 3 class vectors, and they are C1 vector equals E, C2 vector equals D plus F, C3 vector equals A plus B plus C. Let me remind you once again that we are in the group algebra, where the group elements themselves are basis vectors which create a full vector space on which, for example, the regular representation acts. Right now we are not really interested in a representation, we are just interested in the algebraic structure of these vectors. So let us ask ourselves what we can get when we multiply these vectors. When we multiply C1 vector by C1 vector, it's just E star E, and that of course is the identity. So C1 vector multiplied by C1 vector just gives me back C1 vector. So that was very, very simple. And it's easy to see that when you multiply C1 vector by C2 vector, you are going to get C2 vector back. Multiplying C1 vector by C3 vector will give you C3 vector back. A slightly non-trivial example will be when I multiply C2 vector by itself. Now that is of course D plus F multiplied by D plus F. And here you have to remember that this multiplication is the multiplication in the group algebra. This is not the same thing as multiplication of two sets, which we had seen before. In other words, when I multiply this, the standard rules of algebra apply. So this breaks up into four pieces: d square plus fd plus df plus f square. Now of these, d square and f square are both equal to f and d respectively. So the first and the last term in this sum sums up to C2 again. But fd and df, they are both identity. So what you get is twice the identity. So basically C2 vector times C2 vector is twice C1 vector plus C2 vector. Now let me draw your attention to the fact that this being an algebra multiplication, there is a basic difference between this and multiplying two classes as you would multiply subsets of a group. We had already described how to multiply subsets of a group earlier, but there the result would have been a set. Then multiplying the set containing D and F with itself would have given you the set containing D and F in union with the set containing the identity. The fact that the identity occurs twice is something you would not care to worry about, simply because in sets repetition doesn't matter. Here we are doing an algebraic multiplication, treating the group elements or the sum of the group elements as vectors, and so here the p factor 2 in front of C1 is very important. What about C3 times C3? That's of course a plus b plus c times a plus b plus c. This will give you 9 terms in all, but as it's easy to see, of them a square, b square, c square will give you the identity 3 times. On the other hand, cross terms like a, b, b, c, c, a, there are 6 of them. They will give you the 2 rotations in succession, and what you are going to get is 3e plus 3d plus 3f, and that in terms of the class vectors is 3 times c1 plus 3 times c2. Now proceeding along these lines, we can of course see that c1 times c2, as I mentioned before, must be c2. No surprises there. And that's also c2 times c1. c1 times c3 must be c3. And c2 times c3, a non-trivial calculation, will give you twice a plus twice b plus twice c. This takes some amount of work, but it's easy to see that d times a, d times b, d times c are actually other reflections, and if you carry out the whole calculation, this will automatically follow. So c2 times c3 is twice c3, and it turns out that c3 times c2 is exactly the same. Now what we have seen here is a very special case of a general result. If you multiply two class vectors, the result is going to be an integer combination of class vectors. Not only an integer combination, a positive integer combination of class vectors. That is, if you multiply two class vectors for whatever group, the result is always going to be a class vector times some positive integer plus another class vector times some positive integer, and so on, plus other class vectors which will not show up, they will be multiplied by 0. So the coefficients can be either positive integers or 0. In other words, if a class element actually occurs in a product like this, every other element of the class will occur. Not only that, if a particular element occurs multiple times, every element belonging to the same class as that element will also occur exactly the same number of times. Now this is a general property which follows from basic group theory. I will urge you to figure out exactly why this is the case. But let me just state the general statement here. The general statement is the product of two class vectors is an integer combination of class vectors. Well, not just an integer combination, a non-negative integer combination of class vectors. If you multiply Ci by Cj, it's the same as Cj times Ci. That's also something you should really check. What you're going to get, Ck times a bunch of constants summed over all k. These integers must be labeled by the three indices I, j and k. So these are my h, I, j, k's. And as I've just said, h, I, j, k's can only be positive integers or 0. And this is a very, very important property which we will exploit in Burnside's method. In Burnside's method, what we look at is a matrix version of this equation. Ci star Cj is sum from k equals 1 to nc, hi, j, k, ck. If you look at the corresponding matrices, the Ci vectors will correspond to the class matrix Di. So this result actually translates to a relationship between the class matrices in any representation, reducible or irreducible. You are going to get Di dj, the product of class matrices, is going to be simply hi, j, k, dk summed over all k with the same coefficients hi, j, k which came from class vector multiplications. Note that the class vector multiplication can be figured out just by looking at the basic properties of the group itself. You don't need representation theory for that. So here we have matrices which are related to the representations, and the product is given by some constants, some non-negative integer constants, which you can figure out just from the group algebra itself. Now this is true for any representation, but remember, if you are in an irreducible representation, then di, dj, dk, all these matrices would be just Dirac characters, lambda I, lambda j, lambda k for that particular irrep times the identity. And this immediately tells me that for an irrep, you are going to get lambda I alpha times lambda j alpha, which is what multiplies the identity for di alpha, dj alpha, must be equal to sum over all k from 1 to the number of classes hi, j, k, lambda k. Remember, our aim is to determine these Dirac characters for the irreps. And this looks like one equation for each pair of indices I and j involving these irreps. But these equations are quadratic equations, and so we have a bunch of simultaneous quadratic equations to solve, which are not the easiest things in the world to handle. But just by changing our point of view a bit, these equations can be written in a form which should be very familiar to all of you. In order to do this, what we need to do is define a bunch of matrices capital Hi, one matrix for each class, whose jkth element is given by these constants small hi, j, k. So what we have are a bunch of matrices, one for each class, which can be determined simply from the properties of the group multiplication itself. Now, if you look carefully at the right hand side of the expression above, what you will see is that you are summing up over all k the matrix Hi's jkth element times lambda k alpha. So if you define a vector, a column vector, capital lambda of alpha, with elements capital lambda alpha 1, lambda alpha 2 and so on, what we are doing is taking the jkth element of capital Hi, multiplying that by the kth element of capital lambda alpha and summing up over all k. That exactly is a definition of matrix multiplication. So what we really have is that the jth element of Hi times capital lambda alpha is given by lambda I alpha times the jth element of capital lambda alpha, namely lambda j alpha. And this simply can be rewritten as a matrix equation capital Hi multiplying capital lambda alpha is small lambda I alpha capital lambda alpha. And this is nothing other than an eigenvalue equation. What you end up with is capital lambda alpha is a simultaneous eigenvector of h1, h2, h3 all the way up to h and c. And the corresponding eigenvalues are lambda 1 alpha, lambda 2 alpha, lambda 3 alpha, and so on. Put in slightly different language, this means that we can find a single similarity transformation which is going to transform all the hi's, h1, h2, all the way up to h and c, into a diagonal form. And the diagonal elements there will essentially give you the Dirac characters. Well, not only that, if you manage to find this single diagonalizing matrix, the columns of that diagonalizing matrix will give you in one shot all the Dirac characters. Now let us just try to see how this works out in a particular example. And for this, what we are going to do is fall back upon our old friend S3 once again. And because we had already worked out the class products for S3, it should be very easy for us to write down H1. What we will do is we will take one class vector after another and multiply it with the other class vectors. Remember, Ci times Cj is going to be expanded in Ck with Hij as the coefficients, and these are going to give you the jkth element of capital Hi. So, for example, with C1 is very simple. C1 star C1 is C1, C1 star C2 is C2, and C1 star C3 is C3. And here the expansion simply gives us the components of the identity matrix. So H1 is going to be 1 0 0 0 1 0 0 0 1. Now let us consider C2. C2 times C1 is of course C2. C2 times C2 we had already seen before is 2C1 plus C2. Let's take a look at this particular equation. This tells us that H221 is 2 and H222 is 1 and H223 is 0. If you consider the matrix capital H2, then its 2-1 element is 2, 2-2 element is 1 and 2-3 element is 0. Of course, C2 into C3 is 2. C3 tells us that small h231 and small h232 are both 0, there being no C1 or C2 on the right hand side here, and small h233 is 2. Again, these are components of the matrix capital H2. Proceeding this way, we can simply write down capital H2 just by translating the coefficients for each of these products into corresponding rows of the matrix. So, C2 star C1 is C2 alone gives you 0, 1, 0. C2 star C2 is 2C1 plus C2 gives you 2, 1, 0 and so on. Similarly, C3 has these three products which we have already seen before, and this immediately tells us that H3 is going to be 0, 0, 1, 0, 0, 2 and 3, 3, 0. These are going to be the three rows of H3. Now that we have the three matrices capital H1, capital H2 and capital H3, all we have to do is find a single similarity transformation which is going to diagonalize all three together. Now, once we have done that, we can look at the diagonal elements for each of the corresponding diagonalized matrices and they will give you the Dirac characters. Or you just have to take a look at the diagonalizing matrix itself. That will also give you the Dirac characters directly. So the job really is to look for that one diagonalizing matrix, and that will do the trick for you. Now, while it may seem that it is a difficult task to find a diagonalizing matrix which diagonalizes all three together, the job is really not that difficult. All you need to do is keep in mind that usually there is a lot of non-uniqueness about the diagonalizing matrix. This is a result from standard linear algebra. You know that you can change the scales of the columns of the matrix independently of each other for the simple reason that the columns of this diagonalizing matrix have to be the simultaneous eigenvectors of all the h1, h2, h3 that we have in this example. And eigenvectors can be scaled up and down. They will still remain eigenvectors. Apart from that, you can change their order or their sign, and that gives you some amount of freedom in the choice. However, what is very important is if you manage to hit a particular specific capital Hi which has distinct eigenvalues, that is no algebraic multiplicities in the eigenvalues, then it automatically follows that if you manage to diagonalize that one, that diagonalizing matrix is going to diagonalize all three together. To just let you understand what I mean here is H1, for example, is already diagonal, and frankly, if you take any invertible matrix and hit the H1 on the left by that matrix and on the right by its inverse, you are going to get back H1 which is still diagonal. You have infinitely many choices when you are diagonalizing H1. That actually is way too many choices. That doesn't help us at all in finding a matrix which will simultaneously diagonalize H2 and H3. On the other hand, if you try diagonalizing H2, you will find that it has a repeated eigenvalue. As a result, there is a lot of ambiguity about two of its columns, the columns corresponding. There is a lot of ambiguity about two columns of the diagonalizing matrix here, because you can choose any linear combination of the eigenvectors belonging to the same eigenvalue. H3 on the other hand happens to have three distinct eigenvalues, and as a result, when you diagonalize H3, apart from this choice of scale and order in which you write the columns in, there is no further freedom. And any matrix which diagonalizes H3 will automatically diagonalize H2 and rather trivially also diagonalize H1 as well. So, with this consideration in mind, all we really have to do is diagonalize H3. I don't really have to worry about the other two here. Now, diagonalizing H3 is a task which all of you have learned how to do when you studied linear algebra. Of course, the first thing you have to do is find out the eigenvalues of H3, which is solve the characteristic equation determinant of H3 minus lambda I equals 0. Here I, of course, is a 3 by 3 identity matrix. And when you rewrite the determinant out, you will find that it is going to be lambda into lambda minus 3 into lambda plus 3, and this has to be set equal to 0, and this tells us that the three eigenvalues are going to be lambda equal to 0, lambda equal to plus 3 and lambda equal to minus 3, and it is a trivial task to find out the corresponding eigenvectors. So lambda equal to 3 corresponds to the eigenvector 1, 2, 3, then you have 1, 2, minus 3 for lambda equal to minus 3. For lambda equal to 0, you have the eigenvector 1, minus 1 and 0. You must be wondering how we managed to get the scale right here. Of course, if these were just eigenvectors of a matrix, the scale wouldn't matter. Any multiple of an eigenvector is still an eigenvector. However, we want the elements of these eigenvectors to precisely be the Dirac characters, and for that, the overall scale of the eigenvector will matter. If you multiply any one of these eigenvectors by a number, it will still stay an eigenvector as long as that number is not 0, but the components will no longer be the Dirac characters. So how do we know what scale to set? The answer is simple. For each and every irreducible representation, there is one class for which we know exactly what the Dirac character is going to be. And this is the class C1, which consists for all groups of just the identity. So lambda alpha 1, this particular Dirac character, from our general formula has to be NC1, number of elements in this class, divided by small d alpha, the dimensionality of the irrep that we are talking about, times the character corresponding to C1. Now the character corresponding to C1 is always the dimensionality of the particular irrep, simply because C1 consists of only one element, the identity, and the identity is always represented by the identity matrix. And this means that lambda alpha 1 has to be equal to 1. So the first component of our capital lambda alphas, all three of them in this example, has to be equal to 1. And this is what has helped us to set the scale here. Notice that we have three eigenvectors, each of which has a first character equal to 1. Let me remind you once again that this means that for our first irrep, the Dirac characters are going to be 1, 2 and 3 for the three classes. For the second irrep, it is going to be 1, 2 and minus 3. And for the third irrep, it is going to be 1, minus 1 and 0. Please remember that in determining these Dirac characters, all we have done so far is rely on the group algebra to find out the product of the class vectors and then use linear algebra. There was no other group theory involved here. All the group theory, of course, went into the derivation of the basic properties of class matrices and so on. Now, let us just quickly wrap up this lecture by showing you how this calculation of the Dirac characters leads us directly to the character table for S3. So the Dirac character table for S3, of course, is just what I have said right now. You will have 1, 2, 3 in the first row, which corresponds to the first representation. These were the elements of the first eigenvector. Then you had 1, 2, minus 3. Then you had 1, minus 1 and 0. Now what we need to do is first determine the dimensions of the representations. We already know what the answer is going to be, but we are going to ignore our previous knowledge. We are just going to rely on Burnside's method here. And for this, what you need to do is figure out the sum, lambda I square by NCI, because you need to divide the order of the group by that to find out the corresponding dimension squared. And these numbers, when you calculate, turns out easily to be 6, 6 and 1.5 respectively. And if you divide the order of the group 6 by that, you are going to get 1, 1 and 4 for d squares, which tells you that di's are going to be 1, 1 and 2. A result which we already knew, of course. And now that we know the dimensionalities of the representations, we can use the connection between the Dirac characters and the class characters to determine what the character table is going to be. And it is a trivial task to fill in the calculational steps and find out the character table for yourselves. Of course, the character table that you get here is something which you already knew before. But let me point out once again that here we did not have to use any of the individual properties of group elements, like using A dot A is identity or stuff like that. All we did was follow an algorithmic procedure from beginning to end, and that gave us the character table for S3. Now, this particular method, Burnside's method, does not happen to be very efficient and suffers from numerical instabilities for large groups. And there have been several improvements made over this. And there are many other methods for finding out character tables, some of which work better for specific groups. We are actually going to take a look at some of them when we deal with character tables for or representations for specific kinds of groups. But all I wanted to do is impress upon you that you can actually find algorithmic methods for determining character tables. Frankly, in most applications, you don't have to worry about how to find the character table, because the character tables for most useful groups have already been found for you, and you can find them in the tables in the back of a group theory text, or you can search for them on the internet. But given the fact that there are also symmetry groups that you will come across which have not been tabulated, or whose tables may not be available to you, it is important to learn how to find out character tables from scratch, apart from the fact that finding out character tables is really a lot of fun. In the next lecture, we are going to take a look at something which is very important and may have been bothering you a bit. We have been saying that you can always find a basis in which a reducible representation becomes obviously reducible, that is, the matrices become block diagonal, and finding that basis may have immense physical significance. But we have not told you how yet. We are going to remedy that at the beginning of the next lecture. By talking about projection operators, means of changing your basis in such a way that the reduction of a representation becomes trivial. Until then, bye.